Water should not be able to travel through 100 meters of solid bedrock to find the most sensitive machine ever built by human hands. How did a simple 6-meter test hole above the European Organization for Nuclear Research cause an unplanned leak into a tunnel sitting 100 meters underground? This video will answer exactly how a small drilling error revealed a hidden weakness in the rock above the Large Hadron Collider and what it means for the future of physics. The core of this mystery lies in a strange result where lubricating water used for a shallow drill bit vanished from the surface and reappeared deep inside the active particle accelerator complex. We know the rock is supposed to be a solid shield, but this event proved that hidden fissures can bypass even the thickest geological barriers. This means the upcoming 4-year shutdown is facing a reality check before it even begins, because the plan to drill 28 more shafts now requires a total redesign of sealing techniques. By the end of this journey, you will understand why the world's largest machine is uniquely vulnerable to the smallest drops of water, and how engineers are racing to protect 9,000 magnets from the very ground that houses them. The standard story of the Large Hadron Collider is one of perfect isolation and extreme control. We are told that the 27-kilometer ring is safely tucked away deep in the Earth to avoid the noise of the surface world. However, the reality of the upcoming Long Shutdown 3 reveals a different picture, where the machine is constantly at the mercy of the mountain above it. When workers began a small test core drilling only 6 meters deep, they expected a routine sample of the upper soil. Instead, the water they used to keep the drill cool simply disappeared into the earth and began raining down into the tunnel far below. This contradiction between the expected solid rock and the actual porous reality has forced a massive shift in how the high luminosity upgrade is being handled.
This shift is necessary because the stakes involve the most complex cryogenic system in existence, which must stay at a temperature colder than outer space to function. To understand the gravity of this leak, we must first look at the incredible environmental demands of the magnets that line the tunnel. These 9,000 superconducting magnets operate at negative 271 degrees Celsius, which is only a few degrees above absolute zero. At this temperature, the helium that cools the system becomes a superfluid with zero friction, allowing the electricity to flow without resistance. If water from the surface carries heat or minerals into this environment, it can cause a thermal shock that ruins the delicate balance of the sector. The sheer scale of the cooling process means that any interruption is not just a nuisance, but a multi-month delay. It takes 7 weeks of constant cooling just to get one sector down to its operating temperature, and 4 weeks of careful warming to bring it back to room temperature for repairs. Because of these massive time requirements, major work only happens in windows scheduled every 6 years, making the upcoming shutdown in June of the year 2026 a critical moment for the future of science. The plan for Long Shutdown 3 is to physically transform the machine into the High Luminosity Large Hadron Collider. This requires connecting the existing tunnel to brand new underground galleries by boring 28 vertical access shafts from the surface. 14 of these shafts are planned for the area above the Atlas cavern, known as Point 1, and another 14 are scheduled for the CMS cavern at Point 5. The initial 6-meter test hole was meant to be a simple check of the local geology before the heavy machinery arrived to dig the full 100 meters. When the water used to lubricate the drill bit hit a hidden void, it bypassed the expected geological layers and found a direct path to the accelerator. This revealed that the rock is not a uniform block, but a complex network of fissures and cracks that can transport liquid across vast distances. The engineering team was
surprised because the leak occurred at such a shallow depth, yet the impact was felt at the very bottom of the facility. Even though no equipment was damaged this time, the event serves as a warning that the old model of simple vertical drilling is no longer safe for this environment. Every insight loop in this process intensifies the feeling of reverence for the precision required to keep such a monster of a machine running. We are not just talking about a pipe in the ground, but a precision instrument that must align proton bunches with the accuracy of a few microns. The new upgrade will introduce niobium tin focusing magnets that are far more powerful than the current ones, and they are even more sensitive to their surroundings. These magnets are designed to squeeze the proton beams into a tiny area to multiply the collision rate by 10 times. If a leak were to occur during the installation of these magnets, the resulting contamination could set the project back by years. This is why the technical teams have spent the months following the leak updating their drilling and sealing protocols to ensure that every one of the remaining 27 shafts is completely watertight. The mechanism of the leak itself is a masterclass in how small-scale geological features can disrupt large-scale engineering. In a typical construction project, a small fissure in the rock is a minor detail that can be filled with grout. But at the European Organization for Nuclear Research, the tunnel environment is a vacuum that must be kept perfectly clean and dry. The water used in drilling carries grit and minerals that can corrode the outer casings of the cryogenic lines or interfere with the sensitive electronics of the muon chambers. During the CMS experiment upgrades, workers are swapping out the electronics for the drift tube muon chambers to handle higher data rates. These components are essentially high-speed computers that cannot tolerate the humidity or the mineral deposits that come with surface water leaks. The evidence from the test core proves that the mountain is more alive and more unpredictable than the original blueprints suggested. To manage this risk, the engineers are now using a multi-stage sealing process that treats the rock like a fragile antique rather than a solid foundation. They must inject specialized resins into the rock ahead of the drill bit to create a waterproof sleeve as they go down. This adds time and cost to the project, but it is the only way to guarantee that the 9,000 magnets remain in their deep freeze without interference. The transition to the High Luminosity era is a massive undertaking that involves more than just digging holes. It includes the installation of compact niobium crab cavities that will tilt the proton bunches as they cross each other. This tilting ensures that the bunches hit each other head-on, even when the beams are crossing at a larger angle than before. This level of mechanical precision is almost impossible to grasp when you consider it is happening inside a tunnel that was just accidentally rained on by a shallow drill bit. The contrast between the subatomic accuracy of the crab cavities and the messy reality of underground water leaks is what makes this project so precarious. If the beams are not perfectly aligned, the goal of reaching 2,700 proton bunches per beam will fail, and the tenfold increase in data will never materialize. The Awake experiment has already started its own dismantling process as a preview of the massive work to come in 2026. By taking apart the old equipment and clearing the cables, they are creating the space needed for the magnesium diboride high-temperature superconducting cables. These new cables are a key part of the upgrade because they can carry massive amounts of power with much lower cooling requirements than traditional superconductors. However, they are still part of a system that relies on the structural integrity of the surrounding rock. The fact that water could find a way into the tunnel suggests that the thermal insulation of the entire complex must be monitored more closely than ever before. If water can get in, it means the rock is not the perfect insulator we once thought it was, and the heat from the surrounding earth could potentially seep into the cryogenic zones.
This realization changes our understanding of the Large Hadron Collider from a machine that sits in a static grave to a machine that is in a constant struggle with its environment. The old model of a silent and stable underground ring is being replaced by a model of a dynamic and porous geological system that requires active management. The engineers are no longer just physicists and mechanical experts. They have to be master geologists who can predict the movement of water through invisible cracks. The stakes of this work are the highest they have ever been, because the high luminosity upgrade is the final major phase for the current collider. If this phase is compromised by environmental factors, like the ones revealed in the test leak, the future of high-energy physics could be delayed by a decade. This is why the response to the leak was so immediate and thorough, involving a complete review of every meter of the planned drilling sites. We are seeing a pattern of hidden mechanisms being revealed by the very process of trying to improve the machine. Every time we dig deeper or push the magnets harder, we discover new ways that the physical world resists our efforts to control it. The measurement of the water leak was not just a failure. It was a data point that provided a map of the rock's internal structure that no radar could have seen. It proved that the density of the bedrock above 0.1 and 0.5 is not uniform, which will change the way the final 28 shafts are reinforced. This is the forensic logic of modern engineering, where a mistake is turned into a roadmap for success. Now we must address the question that was promised at the very beginning of this video. How did a 6-meter hole cause a leak 100 meters down? And what does the evidence tell us about the safety of the machine? The answer is that the evidence eliminates the idea of a solid, impermeable bedrock shield above the facility. The measurement of the water flow proved that there are vertical fissures acting as natural pipes that can carry surface fluids directly into the heart of the accelerator. While the old model assumed the rock would act as a barrier, the results showed it can actually act as a conduit. The strongest mechanism explaining this is the presence of ancient geological faults that were reactivated or opened by the vibration of the drilling process. This means the interpretation of the tunnel as a perfectly isolated environment is no longer valid, and the remaining shafts must be treated as potential flood zones until they are fully sealed. This verdict changes everything for the viewer, because it shows that the greatest threat to the most advanced machine on Earth isn't a technical glitch or a software error, but the very ground it is built upon. The reverence we feel for this project comes from the realization that humans are trying to maintain a temperature colder than space and a vacuum cleaner than the moon inside a leaky mountain. The clarity we have now is that the Large Hadron Collider is not just a triumph of physics, but a triumph of constant, gritty maintenance against the forces of nature. As we look toward the year 2030 and the restart of the machine, we do so with the knowledge that every proton collision is made possible by engineers who learned how to stop the rain 100 meters underground. The mystery of the vanishing water has been solved, but it has left us with a deeper respect for the fragile balance required to explore the fundamental laws of the universe. If you want to stay updated on how these engineering challenges are met as we approach the long shutdown of 2026, make sure to follow the progress of the High Luminosity project. The journey into the heart of matter is also a journey into the depths of the Earth.
And both are proving to be more complex than we ever imagined. The work continues in the dark, cold tunnels of the border between Switzerland and France, where the hunt for the secrets of the universe is currently being protected by a new layer of waterproof resin and the tireless eyes of the technical teams.